So in this lecture I will talk about approximate energy methods. So now in the syllabus I have already completed the finite elemental methods, that is number 2, and I have completed energy methods, Castiglione's theorem, that is number 3, and I have completed buckling and instability for section 4. I have to complete approximate energy methods and also stress analysis of thick wall pressure vessels and thin rotating discs. So I have to cover 2 sections more. So now today I will be covering most of the chapter 5 contents, that is approximate energy methods. So the topic covered in this lecture is approximate energy methods. So now if you look at the introduction, the approximate energy methods are the basis for modern FEM methods. As you know, we have been calculating the stresses and strains using Newtonian methods, but in this lecture we will consider approximate energy methods because it is less strict. So because it is easier to use, therefore we are considering approximate energy methods. But the idea behind this is to compare and contrast these energy methods with the conventional Newtonian approach. So we have to compare both the energy methods as well as the conventional Newtonian approach, so in order to validate the result. So we will consider the concept of total potential energy. When you look at a rigid system, let a particle move from point A to point B under the action of a net force F, which has a components Fx, Fy and Fz. So basically this resultant force is the sum of Fx and Fy as well as Fz. So if you move from point A to point B, the force components are divided in the X, Y and Z directions. The point moves from point A to point B. Work done by the force F is given by the force and the displacement. So if you integrate the x component of force into the displacement in the x direction, that is du, plus force component in the y direction into dv, which is the y direction, and fz into dw, which is the z direction. So we have to integrate the summative of these 3 elements, and we should integrate it within from point A to point B. If the value of W is dependent only on the position of A and B and is independent of the path taken, then the force F is said to be a conservative force. It follows that the particle returns to A from B via any path including the original value 1, then the net value of W is 0. So now if you consider, if you move the point from point A to point B in any path, the net value of W will be the same. So the net value of W, if you move from point A to point B and if you return it from point B to point A, the net value of W is 0. So the examples of conservation forces are, first one is those due to gravity, second one is those due to the deformation of elastic bodies. consequence of the conservative nature of a given force system is that at any point such as A and B, the particle will have a specific value W associated with it. So if you move from point A to point B, the particle will have a energy W associated with it. This value is called the potential energy. So this value, the energy value that is created from moving from point A to point B, it is called a potential energy. Therefore, VB, which is equals to, now if you look at the potential energy at B, which is equals to potential energy of A, which is VA, minus the integral from point A to point B by integrating these three terms. If you integrate these three terms from point A to point B, and if you substitute it from the VA component, you will get the VB component. So now if you look at this equation, the previous equation, you will see there is a negative sign. So that is very important. The sign convention is very important. So if VB is larger than VA, you will get a negative component. But if the if the energy is if A is above B, you will get a positive component. If a point A is chosen as a datum point for the measurement of potential energy, then VA is 0 and the value at point B becomes V, where V is equals to minus integral of fx du plus fy dv plus fz dw integrated from point A to point B, which is equals to minus W, that is the potential energy, which is equals to the omega. So omega is called the potential energy of the external forces acting on the particle and is equal to the negative of the work done by the forces. Now let's look at the concept of total potential energy. System including the elastic deformation. So let's consider a sample spring under the action of forces F1 and F2. Now as you can see, the original forces are F1 and F2, and from point A to point A to point 2A, they have applied the force at point 1A as F1 and as at point 2A as F2. Now then both of the ends, they displaced at a distance of u1 and also at a distance of u2. So then the same force will remain as the same, but only there will be two displacements in the spring. So basically if you move from if you apply a force F1 and F2, there will be a displacement of u1 and u2. If you look at the work done from point A to point B, now there are two components. So the energy due to the application of force F1 and also energy due to the application of force F2 at point 2A. So now if you integrate this from point 1A to point 1B, let's say for example we integrate from point 1A to point 1B, which has a displacement of u1. So if you integrate from 1A to 1B, F1 plus T, that is the force acting on the spring with respect to the point A and point B. So there is a force F and T is at this F1 and T both are in the same direction. So the force vectors, they add themselves, so F1 plus T. But if you look at the at 2A and 2B, the T component is in the opposite side of F2. So when we are taking the energy, we take F2 minus T, because the sign convention is negative for T. So we can integrate from 1A to 1B F1 plus T into du1, which is the displacement of point from point 1A to 1B, plus point 2B to 2A F2 minus T du2. du2 is the displacement from 2A to 2B. Now if you simplify this, you will get integral from 1A to 1B F1 du1 plus integrate from 2A to 2B F2 du2 minus integral of 0 to u T du, where u is equals to f u2 minus u1 and du equals to du2 minus du1. Now if you look at this, there are 4 components in this topmost equation, since f1t du1 plus f2 minus t du2, there are 4 components. But when you edit them all together, the f1 term and f2 terms will create 2 separate components, and from the t components will add up and it will integrate from 0 to u T du. So basically this part is the summative part. If the original position is taken as the datum, then V is equals to minus W, and we have V, which is equals to integral from 0 to u T du minus 1A to 1B F1 du1 plus 2A to 2B F2 du2. Now if you look at the equation which we get earlier, you can see you can derive this easily. Now integral of T du is the strain energy of the body U. As you know, this is the strain energy of the body, and terms integral F du make up the potential energy of the external forces omega, since hence V is equals to U plus omega, because minus F du is omega. So if you look at the energy equation, the primary energy equation, potential energy is equals to the strain energy U minus omega. So we get V equals U plus omega. Therefore we get the equation total potential energy is equals to strain energy plus potential energy of the external forces. Note that F1 and F2 and T may be variable in respect of both time and position. The body is not necessarily in static equilibrium, and the system need not to be linear, but it must be elastic. We will consider the principle of stationary total potential energy, or which is known as PSTPE, later.